the I stands for amps and the E stands for voltage, the electrical code coach. And my bargain is that these videos you and roll it into a farm load calc. In Article 220 calculations, we're going to be able to round up or down. We're going to round up to the nearest whole number when it's 0.50 and above. And we're going to round down and drop it when it's 0.49 or below. I want to let you know, though, that we're only going to do it one time at the end of the calculation. You're not going to be rounding up and down in between each piece, or you'll definitely end up with the wrong answer. So let's imagine we have this scenario of 26 amps, and after we do all of our math, it equals 32.5 amps. Well, in this case, we're going to round up to 33 amps. Now let's imagine we have a similar scenario, and when we get our answer, it's 31.25. Well, in this case, it's 0.49 or less, so we are going to round down in this scenario. And that's how we're going to deal with all of our numbers in load calculations. When doing Article 220 load calculations, we're going to be using nominal voltages. Although our actual meter reading might be 115 or 130, for our calculations, we're going to be using nominal system voltages like 120, 120, 240, 120, 208. It makes it a lot easier to do these calculations, not having to guess or wonder what the actual voltage readings might be. The first thing that we're going to learn about for our whole home load calculation is how to calculate the general lighting and receptacle loads. This is going to cover all of our general lighting and general receptacles in places like bedrooms, living rooms, hallways, everywhere that's considered a general area. We've grouped all of them together and come up with a very easy way to do it. Now, what I'm getting ready to teach you only applies to residential 1, 2, and multifamily dwelling units. Before we go any farther, we need to define and clarify what is a 1, 2, and multifamily dwelling unit. Well, a single-family dwelling unit, often called a one-family dwelling unit, is exactly like it sounds. It is a single standalone structure or classified thereof. Secondly is going to be a two-family. In our area, we call it a duplex. You may not use that terminology, but this is two homes that are smushed together and classified as a two-family dwelling. And anything that is 3 or more is called a multifamily dwelling unit. It's very important that we understand these definitions because there's some codes that apply in certain areas than others that we have to watch out for. Not only in electrical, but also when we get into building, mechanical, plumbing, and zoning. And these are universal across all these trades. There's a single family, a two family, and a multifamily dwelling unit. The first question we have to ask is, how do we calculate the general lighting load? Are we going to calculate it per receptacle outlet, per lighting? Do we have to count them, add it all up? Thankfully, no, they've made it very simple. So we're going to calculate it at 3 watts per square foot. So for all of the general lighting and all of the general receptacles, all we have to do is take the square footage of the dwelling unit and multiply it by 3. But the code language actually uses VAs. So 3 watts per square foot or 3 VAs per square foot. But the question is, what is a VA? A VA is a volt amp, and for all of our testing, it's equivalent to a watt. So it's true for us to say that 2400 VAs is equivalent to 2400 watts. So for these calculations, we're going to be calculating them at 3 VAs per square foot. When calculating our general lighting and receptacle loads, we will use the outside dimensions of a building or structure. So we're going to measure from the outside of the building, both directions, do our multiplication, and that'll let us know how many square feet we have to multiply by. When calculating our general lighting and receptacle VAs, open porches and garages are not counted in our general square foot VAs. We do not count garages, open porches, carports, and spaces that are not adaptable for future use. How many VAs would you calculate before demand factors? Now, let me stop right there. I haven't taught you what a demand factor is yet, so I'm not going to teach you how to apply it to this part of the load calc because it's really the most complicated, especially if you don't know what a demand factor is. I'm going to teach you a little bit at a time what a demand factor is, and by the time we round back around to teach you how to do it, you'll be a pro at it. How many VAs would you calculate before demand factors in a home that is 1,500 square foot of living space on the main level with a 500 square foot attached garage and a 500 square foot unfinished basement that is adaptable for future use? Step 1 is find what our total square feet that we're working with. So we have our 1,500 general. We will count it. Then we're going to omit the 500 square foot of attached garage. We're going to count the 500 square foot of basement because in this question, it is adaptable for future use. In your testing, it'll say either or, and in the real world, it's almost always adaptable for future use, but you can work that out with your local electrical inspector. So all we have to do is total all that up. That gives us 2,000 square feet. Then we take our 2,000 square feet multiplied by 3 VAs per square foot, and we're going to select D. Great job. How many VAs would you calculate before demand factors in a home that is 2,800 square foot of living space on the main level with a 500 square foot upstairs bonus room and 500 square feet of open front porch? First thing we're going to do is total our square feet. Of course, we're going to count the 2,800 of general, but what about this bonus room business? Yes, we will count the 500 square foot of bonus room. I want to note that the bonus room is a part of the general square foot, but the question makers will put things like this in your test to throw you off. Then we are going to omit the open front porch. We total all this up and we get 3,300. Now we take our square feet multiplied by 3 VAs per square foot, and we're going to select C. Now that we've learned about our 3 VAs per square foot, now we have to learn about what's called our small appliance and laundry circuit VAs. In every whole dwelling unit calculation, we're going to have 2 small appliance branch circuits calculated at 1,500 VAs each, and 1 laundry circuit calculated at 1,500 VAs each, for a total of 4,500 VAs. Now this is something that we're only going to do and attach it to the general lighting load and receptacles before demand factors. We're only going to do it when we're doing a whole house load calc. We are not going to add it on to something like an individual dryer or an individual range. Those are calculated individually. This is only when we're doing a whole home load calc. And once we start doing them, I will make sure to reiterate to you so you understand when and how to apply this. The easiest way to do it is anytime you're doing a whole dwelling unit load calculation is you take your square foot and you multiply it by 3 VAs per square foot. Let's imagine we had this 2,000 square foot house multiplied by 3 VAs equals 6,000 square foot. Then you just tack on the 4,500. It's for the 2 small appliance and the 1 laundry circuit. And you're only going to tack it on if you're doing a whole home load calc. All right, y'all, that's it for lesson 2. You can head over to electricalexamcoach.com to unlock the pro version and all of the quizzes and practice tests. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach, and this is lesson 2.3 at electricalexamcoach.com. Today we're going to be learning about fixed appliances and how they work into a whole house load calculation. Fixed appliances include things like dishwashers in this picture, but it also includes things like garbage disposals, water heaters, central vacuum systems, and microwaves, and pretty much any other appliance once it's fixed. You'll notice in this bottom right-hand picture that there's 2 microwaves. One is not fixed, and the other one is fixed. And when you fix it to the wall or fix it so it can't move, either with plumbing or mechanical vents or anything else, it now becomes a fixed appliance. And there's a special way that they calculate them when doing a whole home load calculation. What it does not include is it does not include dryers or ranges. We're actually going to deal with those separately. So this includes all other fixed appliances except for dryers and ranges. Let's get to it. Before we dive into the calculations, let's learn about demand factors. We're going to be using them for the rest of the program. A demand factor is a multiplier that the code will use to decrease or increase the total calculated demand. The question is, will they use all 4 of these appliances at the same time? And the answer is no. So the code makers have made it so we can reduce the overall demand. Instead of just counting them watt for watt, they've made some multipliers that allows us to reduce the demand that we calculate. And remember, if we have less amps, we could have a smaller service. If we have smaller service, we could have smaller pipe, smaller wire, and a smaller overall cost of the job. The small appliance 75% rule works like this. Where 4 or more appliances are fixed in place, you can apply a 75% demand factor to the total calculated load of the appliances. I do want to note again that this excludes dryers and ranges. We're going to learn how to calculate those separately later in the program. So let's imagine that we have these appliances. And the question is, how do we calculate them all together to turn it into amps and later size our service, which sizes our wire and our pipe? What we're going to do first is find our total connected load. So we're going to go ahead and total all these up, and that equals 6,800. Then we're going to stop and check for demand factors. Step 1 in all load calculations is to get the total connected load. Then we're going to check for demand factors. And in this case, we can apply the 4 or more 75% rule. We take 6,800 multiplied by 0.75, and that gives us a new reduced load of 5,100 watts. And that's what we would take and add to our whole home load calculation. How many VAs would you calculate for a single family dwelling that has the following appliances: a 4,200 VA water heater, a 1,000 VA disposal, and an 1,100 VA dishwasher? First, we're going to find the total connected load. We total all that up, it equals 6,300 VAs. Now, we check for demand factors. In this case, we only have 3 appliances, so the 4 75% rule does not apply, and all we have to do is take our total. I do want to note that one of the 4 choices was as if you had incorrectly applied the 75% rule. In this case, because we only have 3, we don't apply any demand factor at all, and we take the total connected load at 6,300. Great job. How many VAs would you calculate for a single family dwelling in Dallas, Texas that has the following appliances: a 4,200 VA main water heater, a 3,500 VA additional water heater for the basement, a 1,000 VA disposal, and an 1,100 VA dishwasher? First, we're going to find our total connected load. We take and total it up, and it equals 9,800. Now, we check for demand factors. Sure enough, we have 4 or more fixed appliances, so we can apply the 75% rule. We take 9,800 multiplied by 0.75. That gives us a new reduced load of 7,350 VAs. I want to note that if you look at option B, it was 9,800, as if you didn't apply the 75% rule. You got to be careful. Oftentimes, they'll have one of the answers be as if you missed or added one of the steps that you shouldn't have. But you've been grinding, you're going to get it. I know you can do it. And we're going to select C. Let's get to it. All right, y'all, that's it for lesson 2. You can head over to electricalexamcoach.com to unlock the pro version and all of the quizzes and practice tests. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And today we're going to be diving into dryer load calculations. We're going to be in section 220.54 and looking at table 220.54. Let's head there now. When we get to table 220.54, we're always going to read our black bold heading to make sure we're in the right table. Great, I feel like we are. We're going to start on the left-hand side and find our number of dryers. Then we're going to use a straight edge and come over and find our demand factor in percentage. I want to make an important distinction at this point in the program. You have to be very careful with these titles right here. Sometimes they're listed in a replacement value and it just says demand. And in other tables, it'll say a demand factor in percentage. And we've learned that that is just a multiplier. Section 220.54 lets us know that dryers must be calculated at a 5,000 VA minimum or the nameplate rating, whichever is greater. Now, let's learn what a nameplate is. Equipment nameplates. A plate mounted on the equipment or engraved in the equipment that is stating its voltage, amperage, horsepower, and or its wattage. Now, it may only have a few of these, but as we've learned in previous lessons, we can apply Ohm's law to find the unknown. Now that we're dealing with larger wattage appliances, we want to make something clear before we move on. We remember that 1 VA is equivalent to 1 watt, but what is a kVA? In our testing, it's the same as a kW, which is a kilowatt, which equals 1,000 watts. So it's true to say that 1 kVA is 1 kW for all of our testing. Now let's imagine that we have a dryer, and this dryer is a 5 kW. Well, it's also true to say that it's 5,000 watts. And at the same time, if they say that it was 5 kVA, it's also true to say that it's 5,000 VAs. Let's practice converting back and forth very quickly. Let's go from kVA to VA. So if we had 5 kVA and we wanted to go to VA, all we would have to do is take and multiply by 1,000, and that would equal 5,000 VAs. And the same if we wanted to go from VA to kVA, all we have to do is divide by 1,000, and it'll convert it over to kVA. You'll get very familiar with this and won't have to do any multiplying or dividing, but if you ever forget, that's all that you have to do. What is the total VA load you would calculate for one dryer with a nameplate rating of 4,500 watts? First, we find the total connected load. For this, we know that we have to do a 5,000 minimum or the nameplate, whichever is greater. So the 4,500 is gone and the 5,000 remains. Now, we check for demand factors. For this, we're going to head to table 220.54. And we're going to find that 1 through 4 dryers, it's at 100%, meaning that there is no demand factor. And we just select A. Great job. What is the total VA load you would calculate for one dryer rated at 5,200 VAs? First, we're going to find our total connected load. We know that we have to do a 5,000 minimum or the nameplate, whichever is larger. In this case, the nameplate's larger, so we're going to select 5,200. Now that we have our total connected load, we're going to check for demand factors. For this, we head to table 220.54. When we get there, we find that for 1 to 4 dryers, it's calculated at 100%. There is no demand factor. And we're going to select C. What is the total VA load you would calculate for one duplex with one dryer in each unit and a nameplate rating of 4,800 watts per unit? First thing we're going to do is we're going to find the total connected load. We know that it's a 5,000 minimum or the nameplate, whichever is larger. So the 4,800 is out and the 5,000 is in. Then we have to multiply it by our 2 units, and that gives us 10,000. Now we check for demand factors. For this, we head over to table 220.54. And we're going to find that 1 through 4 ranges is calculated at 100%. And we're going to select A. What is the total VA load you would calculate for an 11 apartment multifamily dwelling unit with one dryer per unit and a nameplate rating of 5,000 watts? First, we're going to find our total connected load. We know that it's a 5,000 minimum or the nameplate, whichever is larger. We take our 11 units, multiplied by 5,000, and that equals 55,000 VAs. Now, we check for demand factors. We head over to table 220.54. When we get there, we find the demand factor for 11 is 47%. So we take our original load, multiplied by the demand factor, and that gives us a new reduced load of 25,850 VAs. And we're going to select C. Great job. What is the total VA load you would calculate for a 17 apartment multifamily dwelling unit with one dryer per unit and a nameplate rating of 5,000 watts? First, we're going to find our total connected load. We're going to use 5,000 minimum or the nameplate, whichever is larger. We take our 17 units, multiplied by 5,000 each, and that gives us 85,000 VAs. Now, let's check for demand factors. When we get to table 220.54, we're going to find that it's a 47% base minus 1% for each dryer past 11. So what we do is first have to figure out how many dryers we are past 11. We have 17 dryers minus the 11 base, and that lets us know that we're 6 past 11. Well, what this code is stating is that 47% was our base multiplier, and then what we're going to do is minus 1% for each one that we are past 11. We were 6 past 11, so we're going to take our 47% base minus 6, and that's going to give us a new demand factor of 41%. Now, all we have to do is multiply. We take our original load, multiplied by 0.41, and that gives us a new reduced load of 34,850 VAs, and we're going to select B. Great job. That's the end of lesson 3.1. I want to encourage you and let you know that you're doing a great job and that you can do it. You can head over to electricalexamcoach.com to unlock all of the features in the pro version, including flashcards and practice quizzes. I want to let you know that I offer coaching 100% for free. All you have to do is just email me at electricalcodecoach@gmail.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 3.2 in our video series. Today we're going to be learning about how to calculate ranges and cooking equipment and how they fall into the whole house load calculation. We're going to be in section 220.55. We're also going to be in table 220.55. Let's get to it. When we get to table 220.55, we're going to read the black bold heading at the top of the table to make sure that we're in the right table. Then, starting on the left-hand side, we're going to find our number of ranges. 1, 2, 3, 4, 5, and so on and so forth. Then we're going to notice that there's 3 different columns. They're really in 2 different groups. It's column A and column B are grouped together under the demand factor in percentage column. And the reason that's so important for us to watch out is because column A and column B are multipliers. They're actual demand factors. But column C is a replacement value, and you'll understand more of what that means as we get farther through this video. Starting on the left-hand side in column A, this is when your individual range falls 3.4 or less kWs. In column B is when our ranges, the individual range itself, falls in between 3.5 and 8 3/4. Then column C is when our ranges are 8.76 through 12 kW. Then in the bottom left hand of the table, you're going to see some notes. And that's when we have a situation that doesn't fit into the normal table. And we're going to take it piece by piece. Let's get to it. How many VAs would you calculate for a 9 kW range in a single family dwelling? The first question we're going to ask is, what column does our individual range fall in? Well, ours is a 9 kW, so it's going to fall into column C because it's greater than 8.76, but not over 12. And column C is a replacement value. Now let's find our total connected load. On the left-hand side, we're going to find our number of ranges. In this case, it's 1. Then we're going to cross all the way back over to column C and find that our replacement value is 8 kW. Then, just to stay in practice, I want you to always be familiar with checking for demand factors. But in this case, in table 220.55, column C is a replacement value. It is not a multiplier, so we're just going to select C. Great job. What is the total VA load you would calculate for 3 kW ranges in a dwelling unit? First question we're going to ask is, what column does our individual range fall in? Well, ours is going to fall into column A because the individual range is 3 kW. So we know that we're going to be doing a demand factor. Now we can start from the beginning. First, find our total connected load. We take our 3 multiplied by 3 kW, and that equals 9 kW. Now we check for demand factors. We're going to start on our left-hand side of the table. We're going to find our number of ranges. Then we're going to come over and we're going to find our demand factor. And we find that the demand factor for 3 ranges in column A is 70%. Now, all we have to do is multiply. We take our 9 kW multiplied by our demand factor. That gives us our new reduced load, and we're going to select B. What is the total connected load you would calculate for 2 3.2 kVA cooking appliances in a dwelling unit? First question we're going to ask is, what column does our individual range fall in? Ours falls into column A. Now let's find our total connected load. We take and multiply it out, and we end up with 6.4. Now let's check for demand factors. When we do that, we start on the left-hand side of our table. We come over and find our number of ranges, and then we cross over, and we find that for column A, 2 ranges is 75%. Now, all we have to do is multiply. We take our 6.4 multiplied by our demand factor, and this gives us our new reduced load, and we're going to select A. Great job. What is the total VA load you would calculate for one 7 kVA range in a dwelling unit? First off, let's find out what column we're using. Our individual range falls into column B. Now let's find our total connected load. Well, in this case, it's just one range, so the total connected load is 7. Now, let's check for demand factors. When we head back to our table, we're going to start on the left-hand side and find our number of ranges. Then we're going to cross over and find our multiplier. And when we do that, we find that it's 80% for one range. Now, let's do the math. We take our 7 multiplied by our demand factor, and that gives us our new reduced load. And we select C. How many VAs would you calculate for a 14.6 kVA range in a dwelling unit? Step 1, find out what column our individual range falls in. When we get to column C, we find out that it's only good through 12 kW. When it's over 12 kW, you have to use one of our table notes listed down below the table. In this case, we're going to be using Note 1. Note 1 says that when you have ranges that are 12 through 27 kVA, what we're going to do is increase that column C value by 5% for each kW that we are past 12. Now that sounds really complicated, but I'm going to break it down piece by piece. Step 1 is find your total connected load. In this case, it told us to increase the column C value by 5%. So we start on the left-hand side and find our number of ranges, which is 1, and then we cross over and find the column C value, which is 8 kVA. It wants us to increase that number by 5% for each kW we are past 12. Well, we're 14.6 past 12. And what the code states is that you're going to increase it for each kW past 12 or major fraction thereof. That's just a fancy way of saying if it's 0.50 or greater, you're going to round up. If it's 0.49 or less, you're going to round down. Well, in this case, we're 0.6, so we're going to round up to 15 kVA. So we are 15, and we need to find out how many we are past 12. Well, to do that, we can do some simple math. We have 15. We need to minus the 12 base, and we have 3 left over. Then we need to take that 3 and multiply it by 5% for each one, which is a total of a 15% increase. We're going to take our original number from column C, and we're going to increase it by 15%, and that's going to give us 9.2 kW. The reason that I put the 1 in front of it is because that brought back the 8, and we increased the 8 by the 15%, and it gave us 9.2. And we're going to select A. Great job. What is the total VA load you would calculate for a 3 kVA cooktop and 2 4 kVA wall-mounted ovens in a dwelling unit? First thing we're going to ask is what column do the individual ranges fall in? Well, in this case, we find that it falls into column A and B. This question is very simple. All you have to do is treat the column A ranges individually, the column B ranges individually, and then total them together. So what we do is we find our total connected load. The column A ranges is just 1, so it's 3 kVA. The column B ranges, we have to do some math, and we end up with 8 kVA. Now, we check for demand factors. We head back to our table, and we start on the left-hand side for our column A ranges, and we find the multiplier for 1, and then we start on the left-hand side and find our number of ranges for our column B ranges and find the multiplier, and we're going to find that they're 80 and 65% respectively. Now, all we have to do is do the math. We take our column A ranges and do the math, take our column B ranges and do the math, but then we can't forget to total them back together, and we're going to select A. Great job. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. Today we're going to be calculating HVAC/CVAs for our heating, venting, and cooling. The only code that we need to be familiar with is 220.60, and that's talking about non-coincidental loads. Let me explain what I mean. Usually in a typical house, you're not going to be running the heating and the cooling at the same time. So the code has made provisions for our whole house load calc that we only have to count the larger of the two. Let's get to it. How many VAs would you calculate for an 18.2 amp air conditioner compressor with a 1.8 amp blower and a 10 kW heat strip rated 240 on a dwelling unit? First thing we're going to do is find our total connected load. Let's do our air conditioning first. We take our 18.2 amps and then we add it with the blower motor. That's going to give us 20 amps. Now to convert that over to VAs, all we have to do is multiply. 20 amps multiplied by the voltage gives us 4,800 VAs. Now let's do the heat. We have 10,000 to start with, but then we need to add the blower motor. Our blower motor is 1.8 amps multiplied by 240. That gives us another 432 VAs, and then we total the two together. Now we check for demand factors. There are no demand factors on this, and we will just select the larger of the two, and in this case, it's going to be the heat. We select C. Great job. How many VAs would you calculate for a 28.2 amp air conditioner compressor with a 3.2 amp blower motor and a 6 kW heat strip, all rated 240 on a dwelling unit? First, let's find our total connected load. Let's do our AC first. We take our amperages and we add them together. Then we need to take and multiply that by the voltage to convert it over to watts. And we end up with 7,536. Now let's do our heat. We know that we had 6 kW to start with. Then we need to add our blower motor. We take our blower motor at 3.2 multiplied by the voltage, and that gives us another 768 VAs. We total those two together, and we check for demand factors. There are no demand factors on this part of the code, so we're just going to select the larger, and in this case, we're going to select the cooling. Great job. That's the end of lesson 4.1. You can head over to electricalexamcoach.com to unlock the pro version and all of the practice quizzes. I'm here anytime you need me for free coaching. It's electricalcodecoach@gmail.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 4.2 in our video series. Now we're going to learn how to apply the demand factor to the general lighting load. At the beginning of the program, we learned that it was 3 VAs per square foot, and we had to add on the 4,500 VAs for our 2 small appliance and 1 laundry circuit. At the beginning of the program, I did not teach you about the demand factor for this because it's kind of complicated at face value, especially if you don't know what a demand factor is. But now that we're this far in the program and you are very familiar with using demand factors, I'm going to teach it to you now. And for this one, we're going to head to table 220.42. It's a very important table in our load calculation process. When we get to table 220.42, we always read the black bold heading to make sure that we're in the right table. And it says demand factors for lighting. Now, you can ask the question, if this is the 3 VAs per square foot, well, it includes receptacles. And you are correct. We are allowed to use this table for commercial lighting or any of the lighting in the following locations that we're getting ready to talk about. But we're also allowed to use it for the entire 3 VAs per square foot, plus the 4,500 that we tacked on for the 2 small appliance and 1 laundry. Using this table, we start on the left-hand side and find our location. The first one we find is dwelling units. Then we're going to find hospitals, hotels and motels, warehouses, and really important down here at the bottom, it says all others. So if it's not listed inside of this type of occupancy, we're going to cross over. And if you look over here down in the bottom right hand, it's at 100% calculation, meaning that there is no demand factor for lighting unless you're one of these specific places that are listed on the left. Then over here across the top, we find our demand factor. In this column, it's the portion of the VAs. And then in this column, it is the demand factor in percentage. We're going to break this down one piece at a time and learn how we apply the demand factor to the 3 VAs per square foot and the 4,500 VAs for the small appliance and the laundry circuit. Let's get to it. When looking at this table, we're going to see a multi-layered demand factor for dwelling units. Step 1, we're going to take the first 3,000 VAs at 100%. Step 2, we're going to take in between 3,001 through 120, which is technically just another 117,000 more. And that's how I'm going to refer to it for the rest of the program. We're going to take that percentage at 35%, and then we're going to take anything above and beyond that at 25%. Then step 3, we add them back together. We take the original 3,000 that we set to the side. Then we're going to take that new reduced load, add those two together, and that's going to give us our total load. What is the total general lighting load you would calculate for a 1,600 square foot home, including the small appliance circuits and the laundry circuit in a dwelling unit after demand factors? I want to note